This video is sponsored by PCBWay. More about them later. I like to play chess. Now that's not to say that I'm any good, because I'm not, but I'd like to tell myself that's because I don't play very often. That being a result of my distaste for playing virtually and lack of an opponent who wants to play with me. So to rectify this, instead of spending any time practicing or studying chess, I'm going to make a chess robot capable of beating me so thoroughly that I don't want to play anymore. But to make a self-playing chessboard, there are a few different things I need to solve. First, I need to be able to programmatically determine where the pieces are on the board and communicate the moves I make to a computer. Then I need some way of determining what moves the computer should make, and finally the computer needs the ability to physically move its pieces on the board. Now I've seen some smart chessboards get around this by using indicator lights or a display to show where to move the computer's pieces for it, but I don't think I have the heart to capture my own pieces, so a motion system it is. To make both detecting and making moves easier for the computer, I'm going to be embedding magnets in all of the chess pieces. This can be easily done with 3D printing by designing a hollow in the piece and inserting the magnet mid-print so that it's fully enclosed. When inserting the magnets, I made sure to use the same polarity for all of the black pieces and the opposite polarity for the white pieces so the computer can differentiate between them later. To actually sense where all the pieces are on the board, I arranged an array of magnetic sensors under the board to sense the presence or absence of a magnetic field from a piece above. Now there are other options for sensing the piece locations, like using a camera mounted above the board running image recognition software, but for my design I wanted to keep everything low profile and housed in the board itself. Since there's a sensor for each tile on the board, that leaves us with 64 different inputs that need to be wired to our controller. While there are some microcontrollers with enough inputs for that, they tend to be larger and more specialized than what I'd like to use for this project, so instead I'm going to use a little engineering wizardry called multiplexing. In general, multiplexing refers to combining multiple signals over a shared path. In this case, I'll be grouping the sensors' supplies by column and their outputs by row. So instead of constantly powering all the sensors and having to read 64 different inputs, I'm using 8 outputs to provide power to the sensors one column at a time, and using 8 inputs to read the outputs from each row. This effectively cuts down the required I/O pins to read the entire chessboard from 64 down to 16. Now that we can successfully identify if there's a piece on each tile and differentiate between black and white pieces based on polarity, we have all the information we need to determine the player's moves. If we constantly scan the board and keep a record of what the board's state looked like, we can identify when a piece leaves its tile and arrives on another. Now that we know what moves the player makes, we need a computer capable of making decisions, or more specifically, a chess engine. Since creating a competent chess engine is well outside my comfort zone, I'm going to be running an open source one called Stockfish instead. This conveniently allows me to update the board a move at a time and request what move the computer player would like to make. So all I need to do is create a Python script to act as a middleman between Stockfish and my Arduino. Alright, so high level, here's how it's going to work. I'll make a move that's recognized by the Arduino using the sensor array. The Arduino will then tell the Python script what move I made, which will update Stockfish on the board state and ask for the computer's move. Then the Python script will pass the computer's move back to the Arduino, which moves the opponent's piece to the desired location. So now we actually need a way to move the computer's pieces. Again, the embedded magnets are going to help us here. If we move a strong enough magnet underneath the board, we can drag pieces from one tile to the next. To let go of a piece, you can move the magnet further from the board, so the magnetic field is no longer strong enough to move the piece, but this would add to the size and complexity of the motion system. So instead, I'll be using an electromagnet which can be turned on and off. Speaking of the motion system, there are a few different routes I considered. Initially, I wanted to use an ARM design that would unfold under the board and use inverse kinematics to position the pieces. But after a handful of prototypes, I couldn't get fine enough angular resolution at the joints to accurately and consistently position the electromagnet. So instead, I decided to use a Core XY motion system that's common on a lot of modern 3D printers. This uses 2 motors and a series of cleverly arranged belts to cooperatively position the electromagnet. Now with a little code, I can send the robot a move, for example B7, B5, and it moves to the initial position of B7, turns on the magnet, and drags the piece to the target position of B5. Now it's time to put it all together. Like I alluded to earlier, I'm going to be using some custom circuit boards for this build, courtesy of this video's sponsor, PCBWay. PCBWay is a manufacturing service that allows you to upload your own designs and they make them real. In addition to printed circuit boards, PCBWay offers 3D printing and CNC machining services with amazing capabilities and quick turnaround. For this project, I'm using a custom circuit board from PCBWay for the playing surface itself. I decided to do this for a couple of reasons. Having the chessboard be a PCB lets me route the connections for the sensor array through the board instead of trying to manually wire all the sensors to each other and to the microcontroller. The PCB is also much more rigid than a comparable 3D print, so it won't sag as much on the long, unsupported lengths. Plus, it just looks cool, which is reason enough for me. Thank you PCBWay for sponsoring this video and helping me bring this project to life. Overall, I'm really pleased with how this project turned out. The board is really responsive and reacts immediately after I make a move. The hidden motion of the electromagnet and the slight hum of the motors add some suspense to every move it makes, and the flexibility of the chess engine lets me choose how strong of an opponent I want to face. I've added some exception handling to allow for capturing, castling, and pawn promotion. And I've also added some unique features, like if I make an illegal move, the computer will move my piece back to where it started and let me choose another. With all that said, there are still a few things that could be improved on. For example, when a knight jumps over pieces, I have it programmed to slide in between them, but the magnetic field is strong enough to drag other pieces along with it. This doesn't negatively affect the gameplay, but it just requires me to put the pieces back where they were. But despite that, I think this project turned out amazing, and it gave me a good excuse to start learning to code in Python, which was a bonus goal for me. I have some ideas for improvements on a version 2, including a concept of a really unique motion system, so subscribe if you want to see more, and if you have suggestions, please leave those in the comments below.